All right, so hello everyone. I hope everyone is doing okay. So I'm not expecting many participants. The first lecture after the midterm is usually a bit depressing, but I can assure you, if you're feeling down about the midterm, um, trust me, almost everyone feels the same way. So um, it's not an easy course, and typically this is what happens during the midterm. Is it's a bit tougher than people expect. Um, so don't get too discouraged, because, like I said during the review session, it does get curved at the end, and um, and so what you really need to think of is uh, what you really need to think of is the performance with respect to uh, the average. Um, so yeah. Um, oh well, okay. So if it was easy, then all right. So then I'm happy. Um, um, but maybe not everyone felt that way. So and so for those of you who didn't, then I can assure you that that's normal. Um, and so I have no information about grading or anything like that. So the midterm was on Cole, and so I don't have access to anything on Cole. So you'll get more information about that with the professor. But like I said, uh, whatever your grade is, just take it easy. Um, and oh, oh, that's not fun. Well, he said the pumping lemma wasn't gonna be on the midterm, so that should definitely be something that is uh, raised, a concern that's raised with him, because that doesn't seem very fair. Okay. All right. Well, see, that I didn't expect that. Usually, okay, that's weird. Well, so yeah, so I'm sure I'll talk a bit about the midterm tonight, if not when the grades are released. So you can always ask him about that. So yeah. All right. Well, in any case, so today's tutorial, sorry, is going to be uh, about proving that a language is not regular. So so there are basically two techniques which you've already probably seen to show that a language isn't regular. So the first one is the pumping lemma, which we'll talk about in a second. And the second one is again using the closure properties. So these are the two main ways to show that a language is not regular. And so another very important note is that the pumping lemma should never, so it should never be used to prove that a language is regular, to prove that a language L is regular. So the fact that the pumping lemma holds does not necessarily imply that a language is regular. Okay, so again, like I said before, like I've already said a few times, to prove that something is regular, you have your three main techniques: regular expressions, DFAs, and NFAs, and regular grammars. And the pumping lemma is not something that you can use to prove that something is regular. Okay, so yeah, like it says here, you can use two techniques to show that something is not regular. And so the first technique we'll look at is the pumping lemma. So just a reminder of what the pumping lemma says. So it's stated similarly to how the textbook states it here. So suppose you have a language L, which is an infinite regular language. Then there exists some positive integer M such that any string W in L, so any string W in L, where the length of W is at least M, can be decomposed as XYZ. So take some string W in L, where L is an infinite regular language, then that string W can be decomposed, so meaning can be logically split into, in this case, 3 parts, X, Y, Z, where the length of xy is at most m, and the length of y is at least 1, such that you can pump w up or down. So what do we mean by pump? So we can take y and then duplicate it. So if I is greater than 1, then this is pumping up. And then if I is equal to 0, then this is pumping down. So you can either pump up or down, and whatever you decide, then the pumping lemma states that that pumped string, wi, should belong in L. Okay, so essentially it's giving you a for all statement over I, and it's saying that any way you go, so any direction, if you go I equals to 0 or I greater or equal to 1, then that pumped string should also be in L. Okay, so like I said here, the pumping lemma cannot be used to prove a regular language. So it cannot be used to prove that a language is regular. But because this is a statement, if L is regular, then pumping lemma holds. Then because it's something like this, then if you can show that the pumping lemma does not hold, so if PL does not hold, then, well, typically it's a proof by contradiction, but you can also just use the contrapositive here to make sense of it. So by contrapositive, then if the pumping lemma doesn't hold, then it implies that L is not regular. So this is a high level view. It's not exactly what the pumping lemma says, but this is just to give you an idea of why we're going to use it to show that something is not regular. Okay, so how do we do that? So how do we use the pumping lemma to disprove that a language is regular? So we have to do the following things. So the first thing that we need to do is pick a string W in L. That you know that W is in L, where the length of W has to be at least greater or equal to M. Okay, and so an important thing here that students something get wrong is that they pick a particular length. So they pick, say the length is 72 or 26 or 7. So you can't pick a particular length of sort of a real number. You need to let it be somewhat arbitrary, meaning you need to write the length of your string as a function of M. So the length of your string must be a function of M, okay? So M should not be a fixed value. So that's the first thing you do, okay? The second thing you do is decompose W. Decompose W into your 3 parts, so into your 3 components X, Y, Z, such that the length of xy is less than or equal to M, and the length of y is at least 1. Okay, and so notice here that we're not assuming anything about the length of z, or just z for that matter. Okay, and the third thing, and this is the key part, is that you now need to pick a particular value for I, so a particular value for I, such that when you pump that value, so either down or up, then that pumped string wi is not in L, okay? Which leads to a contradiction. Why does that lead to a contradiction? Because the pumping lemma states that wi should belong to L for every I, right? So if the pumping lemma is for every, and you show that for a particular I, this doesn't hold, then you've proved that L is not regular. All right, so that's the idea. Now let's look at an example. So this one is, right, okay. So we want to use the pumping lemma to prove that L, which is the language that looks like a sequence of zeros and then a sequence of ones, where the number of zeros is strictly greater than the number of ones. So I want to prove that this language is not regular. Okay, so how do I do that? Well, I follow the steps of the proving of using the pumping lemma to disprove that a language is regular. So the first thing that I need to do is I need to pick a string w in L such that the length of w is at least m. Okay, so so now this is the tricky part. The trickiest part of the pumping lemma is finding w. That's usually the most difficult part. So so let's see. Does anyone have an idea of what we could use for w here?
Zero to the m, one to the m.
0 to the m, 1 to the m. So is this
sorry, yeah, m minus 1 maybe.
M minus 1 for the 0 or the 1?
For the 0. Yeah.
For the 1, right?
For the 1, for the 1.
Right, for the 1, yes. I agree, yes. Yeah, because it's for the 1, right? Because of the definition here, right? Okay, good, excellent, yes. So this is a very good, very reasonable pick for w. So now I have my string w, which I know is an L. Okay, good. So now let's decompose w. So what is w? It's a bunch of zeros, right? So in fact, there are exactly m zeros, and there are m minus 1 ones. Okay, so now I know that w has to be decomposed into x, y, z. So xy has to have length at most m, meaning that x is somewhere here, and then y is somewhere here, right? So y doesn't overlap with the ones, y doesn't reach out here, because then that would mean that xy would have length greater than m, right? So the fact that the length of xy is at most m means that xy is, in the worst case, exactly here, right? So then it has length exactly m, but it can be at most m. So that's satisfied, right? This is one part of the decomposition, so it's at most m. And then the other thing is that the length of y is greater or equal to 1. So what does this imply? This implies that y is equal to just a bunch of zeros, right? So let's just say y is equal to 0 to the k, where k is greater or equal to 1. And that's about it. That's about all I can get from my decomposition. So now comes the other important step, is I need to pick an I such that wi, which is x, y, I, z, is not in L. Okay, so maybe let's a question for you. So do you guys think that I should pump up or down?
Down.
Down. Okay, excellent. Very good. Thank you for answering. Yes, so down is right. Very good. So I am going to pump down. So meaning that I'm going to set I equals to 0, right? I'm not going to use, I'm not going to pump up, because if I pump up, what's going to happen? So let's say instead I pump up. So let's say I is 2. Then what I get is I get W2 is X, Y, Y, Z. So that just means that I'll have 0, M plus K, 1, M minus 1. So M plus K is still greater than M minus 1. And so this is still an L. So this does not lead to a contradiction. Okay, so very good. So pumping up would be incorrect. So in this case, I need to pump down. And so the reason why I pump down is now if I have W0, then W0 is X, Y0, Z. So that's X lambda Z, or just X, Z. So then what does that mean? That means that W0 is equal to 0 to the M minus K, 1 M minus 1. So I have M minus K zeros and then M minus 1 ones. So now, now the number of zeros, so if I look at the number of zeros, the number of zeros is M minus K. And because since K, remember, since K is greater or equal to 1, then this is less than or equal to M minus 1, which is the number of ones, okay? And this contradicts this definition here, right? Because here it says that the number of zeros must be strictly greater than the number of ones, right? So that doesn't hold. So this leads us to a contradiction. And so from now on, I'm just going to use, this is my symbol for a contradiction. So I'm going to use this symbol. So I get a contradiction, and that implies that L is not regular. Okay, very good.
Sir,
Yes.
I'm a little confused about the M minus K. Why are we doing M minus K? Shouldn't it be like?
Yeah, no, that's a good question. Yeah. It's the reason why it's M minus K is because here Y is a bunch of zeros, and here I said that Y is exactly K zeros, right? So if I pump down, then that means I initially have M zeros, right? But then I said there's K zeros. I said there's K zeros that belong to Y. So then if I pump down and I remove Y from my string, that means that I remove K zeros from my string. So pumping down just means that I remove K zeros from W1, in fact. And so that means that W0 is, instead of M zeros, it's M minus K zeros. So these zeros aren't here anymore, the zeros for Y. And then you have your ones, right? The ones don't change. So you have M minus 1 ones. And then this difference, the fact that M minus K is now less than or equal to M minus 1 leads to a contradiction.
But sir,
Yeah.
if K was equal to 1,
Yeah.
then it wouldn't necessarily contradict, would it?
Yes, it would, because this says strictly greater. So M minus 1 is not strictly greater than M minus 1.
Okay.
But yeah, you're right. If this was that's a good remark actually. If this was n is greater or equal to j, then you need to think of a different. Then you could use w is 0m, 1m, and then pump down.
Couldn't you just pump twice down? Well, no, I guess not.
No, yeah, that's one of the caveats about pumping down is that the only like you can pump up as much as you want, right? You could set I to whatever you want, but pumping down is the only way you can pump down is just I equals to 0. So yeah. Okay, but good questions. So I hope that's clear. If it's not clear, let me know. Okay, good. So what time is it? All right. So now, yeah. So now I'm gonna do the same thing. I'm gonna ask you what I should do, but I'm not gonna just to save a bit of time. Let's look at this example too. So it's another example of using the pumping lemma to show that L is not regular. However, this one's a bit different from this example here. And actually here, just FYI, I had used a different W in my solutions, but I mean this solution is just as good as this one. So as long as your pick for W makes sense, and then you get a contradiction, then it's good. But what I wanted to say is that this type of exercise or this type of pumping lemma counter contradiction exercise is of the type you get a contradiction because you're working on the number of zeros and the number of ones, or the number of the length of the different parts in your strings, right? In this exercise here your string doesn't have a different part. It's just a bunch of A's. So now what you're going to do, and it's very similar to because there's a lot of different examples that look like this. Like you can have n is equal to like k factorial, or like k square, or square root of k, and things like that. So these types of examples where in fact the language is just a single element, so it's a singleton. These are typically a specific type of pumping lemma exercise where you're going to have to use somewhat of a more numerical argument to disprove that the language is regular. Okay, so what do I mean by that? So let's actually just look at the exercise together. So I want to show that L is not regular. So I'm going to assume, and actually I should have done that in the previous exercise. I'm going to assume, for the sake of contradiction, that L is regular, right? So I assume that L is regular for the sake of contradiction. And so that means that the pumping lemma should hold, meaning that I can use those 3 steps to try to find a way to show that L is not regular. So the first step is I need to pick a string W in L such that W is greater or equal to M. So in this type of exercise where you have something like this, the best choice for M, W is always going to be W is equal to A to the, and then whatever your expression is here. So if it was K factorial, then you would have written M factorial. In this case, it's K cubed, so you're going to write M cubed. So there's probably there's certainly different examples of strings that you could use, but this one's the easiest, and this one's the one I'm going to use. So I'm going to say that w is equal to a to the m cubed. Okay, so clearly this is an L, right? This is an L because my exponent, the exponent of a, is a perfect cube, right? It's m to the cube. Okay, so so that completes the first part. So now the second part is I want to decompose my string w. So w is a bunch of a's, right? And I want to decompose it at x, y, z. So in this case, it doesn't really matter that, right? So the x, y is the first, let's say at most m symbols, and then y is somewhere here. In this case, I don't have to be that careful. It's clear, right, that this is just a bunch of a's. And so I'm going to, again, as before, say that y is a bunch of a's, and I'm just going to, for the purposes of this exercise, quantify the number of a's with k. So I'm going to say, so I pick myself, you could have just said, right, it doesn't matter if it's k, it could be t, it could be q, it could be whatever. So y is a t number of a's where t is at least 1, right? So t has to be at least 1 because the pumping lemma tells us that, so what does it tell us? It tells us that xy is at most m, and it tells us that the length of y is at least 1, right? So y, if y is equal to t number of a's, then t has to be at least 1, and t has to also be at most m, right? It can't be more than m because then xy would have length greater than m, right? So I need, so I have these conclusions from the fact that w is a bunch of a's, okay? So that's what I have. Then the next thing is I need to pick my I. So here, a question for you. Is it better to pump up or down, or does it not matter?
I think we should pump up because we can only, because there's no relationship between like two different variables. We're not trying to show that like the other example that I can, if we follow the pumping lemma, can be lower than j. So I think it's better to go with the side that we can pump more than once.
Okay. Yeah.
Intuitively.
Okay. So that's true, yes, that there's no relation with respect to another sort of variable. But it's not entirely true that you only pump down if you have this kind of relationship, because like I said before, these types of exercises are sort of very similar from one to the other, where when you have a single element in your alphabet. And so typically, actually, in these types of examples, it doesn't really matter if you pump up or down. So I'm going to show why, actually. I'm going to do both of them. So let's say I pump down, right? So I have I equals to 0. So I have I equals to 0. What does that mean? That means that W0 is x, y, 0, z. So that just means it's x lambda z, meaning I have x, z. So what does this mean? This means that W0 is W1 minus k a's, right? So it's W1, which is a m cube, minus k a's, okay? So now I have that W0 is equal to a to the m cube minus 1. So now what I want to do, now my goal is to show that W0 is not in L. So how do I do that? In this case, I need to show, so then in this case, I need to show that m cubed minus k is not a perfect cube. So how do I show in general? Let's say you have what's an example? Let's say you have let's pick the number 7. So you have the number 7. Why is 7 not a perfect cube? Well, you could just say, oh well, it's a small number, it's not a perfect cube, clearly. So you could say that, sure. The other argument that you can give is that it's actually in between 2 consecutive perfect cubes. So it's in between 2 cube and 1 cube. So what does that mean? That means that 7 does not look like an integer cube because the 2 consecutive integers that would make sense here, it's in between them, right? So clearly I can't have something like 1.5 cube, right? So that wouldn't make any sense. And so because 7 is not equal to something cube, or rather because it's not equal, because it's in between 2 consecutive perfect cubes, then this implies that 7 is not a perfect cube, right? And so that's the strategy I'm going to use for this number as well. So let me move this here. Okay, so I want to show that m cubed minus k is not a perfect cube. So in fact, what that means is I want to show that m cubed minus k is strictly less than m cubed and strictly greater than m minus 1 cubed, right? Because those are the 2 consecutive cubes between which this number seems to fall, right? So to prove 1, so to prove 1 is quite straightforward. You have m cubed. Because I know that k is at least 1, then m cubed has to be strictly greater than m cubed minus 1, right? And minus 1 is greater than or equal to minus k. So then that means that m cubed minus 1 is greater or equal to m cubed minus k. So m cubed minus k has to be strictly less than m cubed. Okay, so that's how you would prove 1. And then how to prove 2. So how to prove 2. So 2. I want to show that m cubed minus k is strictly greater than m minus 1 cubed. So I might mess up the formula for, so I have m minus 1 cubed. So what is this? This is m cubed, I think minus 3m squared. Plus, I think it's this, but it doesn't really matter what it is because either ways you would get. So this I'm not quite sure if this is exactly right, but it would give you an expression like this, right? No, actually, I think this is probably right. So you have m cubed minus 3m squared plus 3m minus 1. That's the cube of m minus 1. Yeah. So I think this is right. And so then what I can show is that if I have this number, then this is clearly going to be smaller than wait a second. Or no, sorry, greater, right? Yeah. So this is clearly going to be greater than m cubed minus k, and so I'm not gonna show this in detail because then this would require a proof by induction, which I don't particularly want to do. But then you would get this conclusion by doing a proof by induction to show that m cubed minus k is strictly greater than m minus 1 cubed. And so because you have that 1 and 2 hold, it means that m cubed minus k is between two consecutive perfect cubes, meaning that, so 1 and 2 both imply that, so they both imply that m cubed minus k is not a perfect cube, which implies that W0 is not in L. Okay, so then pumping down works. It shows that you get a contradiction, right? So it means that L is not regular. And so just before, because I'm sure someone has a question, but just before a question, I can also show that pumping up would work just as well. So if I pump up, then W2 is, I add an extra K. So I have A m cubed plus K, right? And then it's very similar. I just need to show that m cubed plus K is strictly greater than m cubed and strictly less than m plus 1 cubed. And actually this way is a lot easier to prove because you don't have to get mixed up with negatives. And you don't actually need to use, so this one actually doesn't require induction to prove. All right, and so in both cases, if you prove it, if you pump up or down, your resulting length is not going to be a perfect cube. And so in both cases, you'll get a contradiction. And so in both cases, this leads to a contradiction. And then this implies that L is not regular. All right. So is there a sequence? Yes. Well, okay. So it still seems very abstract. So this is, so this sequence is the one that I usually use. The reason why it probably still seems abstract is probably one, just you need to do maybe a few more examples. And then the other thing is because the pumping lemma is a very abstract concept, because you're the one that has to create. So it's kind of like a constructive proof, because you have to create your own W, right? So it's not like a typical 232 proof, in the sense that you're given your if, and then you show your then. In this case, you kind of have to create your own if, and then with your creation, you have to show a contradiction. And so I think it's very normal at the beginning that you find it abstract, but then with a few more examples and just because usually this is the hardest part, right? Finding W is probably the hardest part. And then picking I, you can typically get an easier hang of it. So if you're given a W, then it's a lot easier to pick the I yourself. But picking the W might be a bit harder. So that's why doing a couple more examples would probably help in making it less abstract, I think. All right, so yeah, so any questions, any other questions about this before we go to closure properties? No questions? All right. So now closure properties to prove that a language is regular. So again, the same idea. You're going to use a proof by contradiction. So you're going to assume that your language L is regular, but now you're going to use the closure properties. So you suspect that L is not regular, and so you assume that it is. And then you know that closure properties, that regular languages are closed under the union, the intersection, the difference, and so on. And so then the idea is you take L and you use language operations so that you preserve regularity, and you construct a language. So you construct a language L prime where you know already, so you know that L prime is not regular. And so that's going to lead you to a contradiction. So for instance, well, actually, let's go to the example. So the example is actually quite good. So for instance, I have this language here, ANBN for n greater or equal to 335. So I want to show that this language is not regular. So what I'm going to do is I'm going to assume that L is regular, right? So L, for the sake of this proof, is regular for now. Then I'm going to combine it with this language L1 ANBN such that n is less than 335, right? We already saw this language, and we saw that because it's finite, right? Because it has 335 elements, it is regular, right? So L1 is regular, okay? And I assume that L is regular. So that means that if I take L and I take the union with L1, so this is a regular language, this is a regular language, and so the union is going to be regular. But now what do you notice? You notice that the union is actually ANBN for n greater or equal to 0. And this is telling me, right, the closure properties is telling me that this language is in fact regular. But as you saw in lecture, ANBN is not regular. So we know that it's not regular, and hence this is a contradiction, right? So we have a contradiction, meaning that our initial assumption, so that means that our initial assumption was incorrect. Our initial assumption was incorrect, which implies that L is not regular, right? Because our initial assumption was that L is regular. So if that's incorrect, then that means that the opposite is correct, and so L is not regular. Okay, so that's an example. That's an example of what I meant by you construct with L a language L prime that you know should not be regular. Okay. Questions about this? No. Okay, so let's do another one. This one's a bit more complicated. So I want to show that the language L, which looks like a string, C, a string, where the first string is different from the second string. So I want to show that this language is not regular, right? And so maybe intuitively, why is this not regular? So just if you follow intuition, is because you need memory, right? So you need some memory to remember what W1 looked like so you can compare it to W2. Okay. So that's why it's not, it doesn't seem to be regular, right? Okay, so we know this, right? We know that we suspect that this is not regular. So then what do? We're going to prove that it's not regular using the closure properties and also the pumping lemma. So let's assume that L, for the sake of contradiction, is regular, okay? Right, so I'm assuming that L is regular. And so by the closure properties, if a language is regular, its complement will also be regular, right? So the complement, so now what does the complement of L look like? So the complement of L is going to be for one thing, it's going to be the complement of this, right? It's going to be all of the strings that look like W1, C, W1, such that W1 is in AB star. Whoops. So that's going to be the first part of the complement, and then union, and it's probably going to be a bit complicated to write out the complement, so let's just say something else, right? So this is your complement. It's W1, C, W1, so the same string on the left and the right of C, union some other stuff, okay? And so the reason why I don't care about the some other stuff is because now I'm going to combine this language L complement with another regular language, right? So I'm assuming for the sake of contradiction that L is regular, so L complement is also regular. So now I'm going to take L complement, and what I want to do is I want to find a language where I think it'll be quite easy to show that that language is not regular using the pumping lemma. And so one way to do that is if these strings here, if this same string could only be over a single string or a single symbol in an alphabet, right? So if this was, say, A-N-C-A-N, so if this was A-N-C-A-N, then it would be pretty easy to show, or, quote unquote, pretty easy to show that this language is not regular using the pumping lemma. Okay, so what does that mean? So that means that if I take L complement and I intersect it with, well, I'll intersect it with just that. I'll intersect it with a bunch of A's, C, a bunch of A's. So I'll have A star, C, A star, right? Then this must look like AN, C, and then AN, because C is not a symbol of the alphabet, right? It's just an additional symbol. And then to the left and the right, I need to have the same exact string. And with this intersection, the left and the right of the string has to have just a bunch of A's, right? So then my new condition is just such that n is greater or equal to 0. Okay, so I have that, right? So far, what's the logic? The logic is I said L, I assumed for the sake of contradiction that L is regular. So L complement is regular. So then L complement intersect A star, C, A star. This is also regular by my assumption, right? So now I need to show that this is not true. I need to use the pumping lemma. So I need to use the pumping lemma to show that AN, CAN for n greater or equal to 0 is not regular. Okay, so I'm not going to go through the details of the pumping lemma again, but what would be an example of a string W that I could pick? So let's say M is the pumping length, right? So the integer in my pumping lemma. Then what could be a possible string to show that W is to use W to show that L is not regular for this language? Let's think about it.
AMCAM.
Yes, thank you. Very good. Excellent. So it's very similar to like BN, sorry, where it's kind of like an obvious choice that it should be AMBM. It could be something else, right? It could be AM plus 1, BM plus 1 for that example. But the easiest case for that example, and also for this example, is just going to be AMC AM. Very good. So then clearly the length of W is, well, in this case, it's M plus 1. So it's clearly greater or equal to M. And then you can see here that I can either pump up. So I would get, let's say W2 would be A M plus 1, or M plus K, sorry, M plus K C A M. So this would obviously lead you to a contradiction because M plus K is different from M. So that's if you pump up. And then if you pump down, so W0 would be A M minus K C A M. And then this would still lead to a contradiction because this number is different from this number. Okay. Yeah, so pumping up would work, right? And then pumping down could also work. Right? But of course, it's, I mean, there's no, right? There's no preference. It's just sometimes there could be a question like in a test or whatever, where it's, I should only pump up, I should only pump down and things like that. And then in this case, you could see that pumping both up and down could work. Okay. So then what does that mean? That means that AN, whoops, ANCAN, such that n is greater or equal to 0, is not regular, which is a contradiction, right? Because by this assumption, I had that it was regular. So this is a contradiction. And so this means that L, so our initial language L, which was W1, C, W2, such that W1 is different from W2, is not regular. And so you can notice that here, actually, it would be quite difficult to find a string W to pump up or down, right? So it'd be quite difficult here to find such a string. But using the sort of the closure properties, you get to kind of an easier pumping lemma exercise. Yeah, so why did I intersect with A star C A star? So I intersected with that, with this string, right? I intersected with this string because I wanted to get an easier language to disprove that it was regular. So this language, it's a lot clearer what W should be, right? What you should pick as W, so that you can disprove that a language is regular. Here, it's not quite obvious what your string should be, right? Yes, exactly. Yes, very good. Because regular languages are closed under the intersection. Very good. Excellent. Okay, good. So any other questions about this? This is a good, I think this is a good example. No question? All right, so an exercise for you. I'll give you a minute. Use the closure properties to prove that the language L is not regular. So let's check back at 5:08. All right. So I wanted to prove using the closure properties that the language L, here, hopefully you all assume that sigma star was 0, 1 star. Sorry about that, it should have been specified. Right, such that W has more zeros than ones is not regular. So any ideas of what I could do here? Isn't this the same? Ooh, yes. Okay, very good. Very good. Excellent. So yes, there was a reason why we did that exercise. Okay, so it's kind of the same, right? Because in this exercise, it's a bunch of zeros and then a bunch of ones where the number of zeros is greater than the number of ones, right? So this isn't exactly the same as this question, right? Because here it could be 0, 1, 0, 0, 1, right? So the zeros and the ones can be sort of intertwined. Okay, but how does this example help us to solve this example? We use the union. Okay, so let's say we assume that L is regular, right? So we use the union with regular language to get, so it doesn't need to be the union, right? So, okay, good. So it doesn't need to be the union. It could be the intersection, the difference, the reversal, any operation, right? So in this case, if you take your language L, and then you intersect it with L 0 star 1 star, right? Then this will give you 0 to the n, 1 to the, let's say, m, such that n is strictly greater than m. And then because regular languages are closed under the intersection, it would imply that this is regular. But as we showed, right, we just did an exercise with this. This is clearly a contradiction. We know it's not regular, right? And so what does this imply? This implies that L is not regular. Okay, very good. Very good. Come in. So last exercise for you before I let you go. So given the language L, we have the following language and an integer m from the pumping lemma. Which of the following strings for W would be a suitable choice to show that L is not regular? Okay, so this one again, I'll give you a minute and we'll look at it together. All right. So this question actually wasn't particularly well done, to be honest, because if you go through each of these selections, so let's look at this first one. You have AM, BM, CM, right? So this already does not belong to L, right? Because this language definition says that the number of C's should be the number of A's plus the number of K's. So in this case, this should be 2m, right? And then if this was 2m, then it would be a good candidate if you had 2m, right? Then it would be perfectly fine. Then you could pump up, and then you would show that the sum wouldn't equal to m, which is a contradiction. Right? Pump up or down. Here again, this doesn't even belong to L because C is 0, right? So again, you could have, again, if this was 2m though, it would have been fine. This language as well. Yeah, so this is a bad example. So here you have m plus 2m is equal to 3m, right? So that's clearly not equal to m. So this doesn't even belong to the language. So that's not a viable option. So then the only viable option is actually this one, because this one does belong to L. And then here, I could pump up or pump down. If I pumped up, I could get, let's say, a m plus k c m. So that would lead to a contradiction, right? Because you would have b to the 0, so then m plus k plus 0, that's not equal to m. Or you could also pump down. So a m minus k, b0 cm. So this also leads to a contradiction because m minus k plus 0 does not equal to m. So let's say, let me give you an extra option. Would this have worked? dm. Because this one actually does belong to L, right? Does this help me? No, very good. It doesn't help me. Why? Am I asking you or am I asking myself? Well, does anyone, can you answer why, Jonathan? Don't want to put you on the spot, but yeah, okay, very good, excellent, yeah. So like you just said, because it doesn't matter if you pump down or pump up, no matter what you do, the pumped string wi will belong to L. So then you'll never get a contradiction. Yeah, very good. So it will always be valid. Yes, excellent. Well said. But this is, so these two types, so like this type and this type would be invalid choices for W. First of all, you have to make sure that your string is in the language. And second of all, you need to make sure that if you pump it, there's a particular setting for I where you will get a contradiction, right? All right, very good. So we actually finished relatively early. Well, like in my terms. Yes, I can. So I was gonna say if there are any questions. So sorry, I mean, can you explain why pumping up C? Yes, yeah, sure. So so you have W is equal to AMCM. Whoops. AMCM, right? So then pumping up, yeah. So if I pump up, so let's say I pick I is equal to 2, then I have W2 is, well, let's say, so I'm going so this would be step 1, right? Let's suppose that this is very formal, right? You have a bunch of text. Step 2 is Y is just A to the K, right? And then, so don't do this in your assignment, please. Just actually do it formally, but just for the sake of explanation, I'm doing it like this. So I have W is AMCM, Y is just a bunch of A's. It's in fact KA's. So now if I pump up, then I have X, Y to Z. So I have X, Y, Y, Z, meaning that I'm adding an extra Y. So I'm adding an extra KA's to my string. Okay, so why is this a contradiction? Because now if I look at AM plus K, okay, so right, so AM plus K, B0 CM, right? So the number, this definition says that the number of A's plus the number of B's should equal the number of C's. But yes, excellent. As you said, this is not true because m plus k, k is at least 1, so this is greater or equal to m plus 1, which is strictly greater than m. So then this means that we have a contradiction. Okay, very good. Yeah, yes, excellent. I like that mentality. All right, any other questions? Oh, by the way, oh yeah, for assignment 2, I have, I think, four like sub questions left, and then we'll be able to release the marks. So far it's been not bad. I haven't marked the question with the sort of the duplicate, so the one where it's like dupe of the language. So I don't really look forward to marking that one. But in general, those are typically the hardest questions in 335. So right, so it's fine if you didn't fully understand that question. Well, it's not fine, but it's fine if you didn't do that well on the assignment, but then try to understand it in the solution. All right. Any other? Well, that wasn't a question, that was a comment, but any other questions? Okay, no, it doesn't look like it. So all right, so like I said, don't get discouraged, everyone. It's gonna be okay. So have yourselves a nice lecture, and I will see you on Wednesday. All right, take care, everyone. Bye-bye.